Hello guys, and let's continue our journey through differentiation. And today I would like to show you something which I call for my students always bad boys. These are three functions where we are not having the properties of a differentiable function. The first is the hyperbola 1 divided by x, the second is the square root of x, and the third is the absolute value of x. And we quickly see what's happening and where is the trouble if we're going to produce derivatives for these three functions. So first of all, let's start with f of x being equal to 1 divided by x. Let's consider the graph. We see that the function is broken at 0 and it's really torn apart. So you see it's not possible to compute the value of 0, otherwise we'll be dividing by 0, which is not possible, as you remember. And so it's kind of clear that approaching this function through a tangent line at 0 could be also difficult, rather impossible. But on all the other spots, instead of but 0, we can easily approach the function by the tangent line. So let's check it. F prime of xo is a limit h towards 0. The first principle, we got 1 divided by xo plus h minus 1 divided by xo divided over h. This is how it starts. Now you should be familiar a little bit with the fractions. It's kind of very important everywhere in mathematics or in life. We multiply it times 1. Multiplication times 1 isn't changing anything, so I multiply in this case times xo divided by xo, and in this case times xo plus h divided over xo plus h. Now see what's happening. If we have a minus in front of a fraction, if we have, for example, minus a plus b divided over c plus d, that means basically we have minus 1, which is multiplied times a plus b divided over c plus d. I can rewrite minus 1 as minus 1 times 1, firstly. And then we know how to multiply fractions. This is numerator times numerator and denominator times denominator. Now you hear some music from the police. I'm not in New York City. I'm in Turkey right now, but everything is cool, no worries. So we have minus 1 times a plus b and multiplication times minus 1. Distributive law basically changes the signs of every expression inside the parentheses. We have minus a minus b divided over c plus d. This is the first way, but we also could have written minus 1 differently. Look here, we can write it also as 1 divided by minus 1, which is a plus b divided over c plus d, which is 1 times a plus b divided over minus 1 times c plus d. So we have a plus b, and now we change the signs in the denominator, as you can see right there. So they are both equal, but which is more preferable? Which is better for us? Well, for us, for our purposes in this question, the first expression is better. This one is better because we're not changing the denominator and we could add the fractions. But normally it doesn't matter. It's important for you to understand that both cases are valid, and it's not absolutely 100% sure that you are applying the minus sign in front of the fraction only for the numerator. Both possibilities are given. So we're applying it here, this minus for the numerator. I love Microsoft. Oh, very nice. So very nice. We have now xo minus xo and minus h. I'm changing in both cases the numerator. I have xo times xo plus h, and I divide it by h, which I can write as h divided by 1. We have a limit h towards 0. Now you see those two are gone. We have minus h divided over xo times xo plus h times 1 divided by h. We can cancel those two. And at the result, we have a limit h towards 0 minus 1 divided over xo times xo plus h. And if h is now infinitely small, we have no troubles to let it be 0, and the outcome would be minus 1 divided over xo squared. So our assumption was correct. The function isn't defined at 0, and it's not possible to produce a value of derivative of this function at 0 either, because we will be dividing by 0 squared. So far so good. This is the first bad boy. That means if the function doesn't leave at a point, it's not possible to describe this function well enough with a tangent line. Alright, the first bad boy is done. We can also do it with the x method. It's rather the same. So I see no big difference here. Let's do maybe the x method now for the square root. Alright, so if you guys are not that sure about the x or the h method for these examples, just let me know down in the comments, and I'll change it easily, no problem. This is pretty easy. So f of x equal to square root of x. The first derivative, let's apply, as I mentioned previously, the x method in this case. So we have a limit x towards xo. This is square root of x minus square root of xo divided over x minus xo. And if you remember, the graph of the square root looks like this, kind of shifted parabola. And as you can see, this is the positive slope. This is steeper positive slope, even steeper positive slope. But at 0, this is very steep. Infinity steep, I would say. So m is equal to infinity. And well, infinity is not a good kind of symbol to work with as a number. It's not possible, I would say. So because if you consider infinity as a number, you're going to get into trouble, as you can see. Subtract infinity on both sides. 1 equals to 0. There you go. So we get in trouble here. It wouldn't be working this way. So rather than do this. So maybe we have some trouble at 0 here. We will see. Yes, we do. But we have no trouble for the function at 0. Square root of 0 is easily 0, since 0 times 0 is 0. So everything is cool. But maybe with a slope. Yeah. And we will see it in a moment. Remember that you can write 9, square root of 9, squared as 3 squared, which is 9. So basically every positive number can be written as square root of the number squared. We're not changing anything. Let's do it here. We're only defined for positive values or 0, where this is applicable. And now we can apply the binomial formula in the denominator, as you can see. So we have square root x minus square root of xo, and divided by square root of x minus square root of xo times square root of x plus square root of xo. We can change it, we can cancel it, and now we have a limit x towards xo, 1 divided over square root plus square root of xo. Now x is approaching as o, and now we have 1 square root of xo plus 1 more, and this is 1 divided by 2 square root of xo. That's it. Alright, and as you can see, we have a trouble producing the derivative at 0, because we would be literally dividing by 0. Not possible. Second bad boy. Gotcha. And now the third one, pretty easy. F of x equal to absolute value of x. So what is the graph of the absolute value? Well, the absolute value is never negative, so if the value of x is positive, no problems. But if the value is negative, in order to make it positive, we just put a minus in front. That's the story. Alright, so what's the graph? It looks like this. Bam. Bam. So this is x here, and this is minus x there. The slope here is minus 1, and the slope there is plus 1. So outside of 0, everything is cool. But on the left hand side we have minus 1, on the right hand side we have plus 1, And if we are at 0, well, we cannot approach 0 from the left, neither from the right-hand side, because there is a huge jump in the slope value between -1 and 1. There is nothing in between. So the uniqueness is not given. We cannot approach it from left and from right and have the same results. They would be always different. And that's why the function at this point everywhere, before 0, it has the slope of -1. So the first derivative, let's say at -7 would be -1. At 12 it would be 1. But just at 0 it isn't working. So f prime at 0 isn't given because this value isn't unique. From the left-hand side -1, from the right-hand side +1. We go deeper into calculus and we will see actually that if we produce derivatives, the derivative of this function is -1, then we jump, and then we have +1. So this value is being taken, this is cut off. Alright, and now we see that the derivative of the absolute value of x isn't continuous. It's going to be kind of important argument for later on proofs. Alright, so 3 bad boys. 1 divided by x, square root of x, and the absolute value of x. So what is important for us? A function is differentiable at xo if we have a limit. Doesn't matter which one we prefer. Let's say again first principle, the h-method. If it's computable, if it exists, is unique and finite. Remember, unique, absolute value of x was not unique, 1 bad boy. Finite, square root of x was infinite, slope at 0, and must exist. If it doesn't exist like it with hyperbola, with 1 divided by x, we cannot approach it. Alright, I hope it helped you guys. Thanks for watching. And see you in the next videos. Bye bye. Have a good time.